Yes, let's start. And then let's give the upper triangular matrix. What's the upper triangular matrix? Our matrix should be square, first of all. It's okay. Square matrix A. And also A and greater than J, and the all entry should be 0. And what does it mean under this one? First row, A sub 1 1, A sub 1 1, 1 2. It's okay. This one. Look at this matrix. It's okay. Sorry. Look at this one. A sub 1 1, 1 2 1, and the next one, and this entry and the second row, first column, second row, first column. So, and this entry should be A sub 2 1 is 0. It's okay, is 0. And the next one 2 2, not satisfy this one. So A sub 2 2, and the next one, and the 2 and the last one, and the next one, this one 3, and the row 3 and the column 1. So A sub 3 1 is 0, and also this one is 0, and the next one, this one should be 0, because what's the entry in the located in and the third row, and the third row, second column. So this one should be 0, and this one is 0 0 0 0, and so we obtain and this matrix, this one, and the form, and this one is, this part should be 0. So if our matrix is in this shape, and this one, this part should be 0. It's okay. This one is upper triangular matrix. It's okay. Upper triangular matrix. So let's define the lower triangular matrix. So, and it should be first square matrix, yes, and also if A less than J, I less than J, all entries should be 0 for all ij. So, and means this part should be 0. It's okay. This one is lower triangular matrix. It's okay. Lower triangular matrix. So look at our example. And this matrix, square matrix, yes, because 3 by 3. It's okay, square matrix. Should be square matrix. And also this part 0. So this one is upper triangular matrix. It's okay. Upper triangular matrix. So, and also let's give the example lower triangular matrix. For example, 1 0 2 3. Look at this one. This one is lower triangular matrix. It's okay. So it is one more question. And it is possible to get an upper triangular matrix and lower triangular matrix. It's okay. And let's give an example. It is possible, and some one matrix, but these matrix should be upper and lower triangle. It's possible or not?
Yes, it is possible.
So what can you say about the, let's give an example.
The square zero matrix, maybe.
This one? This one is upper triangle and lower triangle. It's okay? It's true?
Yes.
Yes. So, in general, what can you say about our matrix is upper and lower triangular matrix? These matrix should be, yes, complete this sentence. Our matrix is upper and also lower triangular matrix should be
Zero matrix.
zero matrix
And square.
and square. And every zero matrix, upper triangular and lower triangular matrix. It is true. Every zero matrix is upper
Yes.
and lower triangular matrix.
No,
No, what's the reason? Because
maybe they may not be square matrix.
square matrix. Look at this one. Zero matrix, yes, but not square. So first condition not valid. It's okay. So this one is not upper triangular or lower triangle. So and what's the statement? Statement should be and every square zero matrix is a upper and lower triangular matrix. It's okay. Every square zero matrix, upper and lower triangular matrix. It's true.
Yes.
Yes, it's true.
Also, diagonal matrix is the same, right?
Your answer is in the every diagonal matrix, upper and lower triangular matrix?
Yes, it is.
Yes, everybody, it's true. This one? Yes, every diagonal matrix, upper and lower triangular. Let's come back diagonal matrix. For example, this one. Look at this one. Look at this one. This one is diagonal matrix. And look at this part is 0. Yes. And also use a different color. Maybe look at this one. This one is 0. Yes. Upper and lower triangular matrix. So, and our statement is, and every diagonal matrix is a upper and lower triangular matrix. It's okay. And also, every scalar matrix is upper and lower triangular matrix? Yes. It's okay? It's true. Every square zero matrix, square, it is important, is upper and lower triangular matrix. And also every diagonal matrix is upper and lower triangular matrix. And this one is, if we can write in general case, this one is true. What's the reason? Every diagonal matrix is upper lower triangular matrix. Yes, it's true. And also we know that every square zero matrix is a diagonal matrix. Yes. And this statement contains and this one. It's okay. You don't have to write this statement, because this one is a specific case of the diagonal matrix. It's okay. If we know that every diagonal matrix is upper lower triangular matrix, it's true, and we know that every square matrix, square zero matrix is a diagonal. So we can obtain then the second statement. This one is true. It's okay. And also every scalar matrix is a diagonal. Yes. So, and the special case and also gives another case, every scalar matrix is upper lower triangular matrix. Yes, it's true, because every scalar matrix is a diagonal matrix. So it is enough to say that in general, and these statements contains all of them. Every diagonal matrix is an upper triangular matrix. It's okay. So we obtain and this one, this statement, and also this statement, and also consequently we obtain every scalar matrix is upper and lower scalar matrix. It's okay. Any question? Okay. Now let's define and let's give this next definition, and take the two matrices and they have to say that and these matrices the same are equal. It's okay, are equal. Sorry. And take the R matrix A and matrix B, and the R matrices should be n by n matrices, have the same dimension, not different. This one is n by n, this one is n by n. It's okay, n by n. So A and B are said to be equal if and the corresponding entry of matrix and it should be and the entries of the matrix P, the corresponding entry. So look at the next example. It's okay. Our example. Let's give an example to understand that it is one. It's okay. Matrix A and this one, matrix P. It's okay. So question is here. A and B are equal, and if what's the x and y and z? Look at the A and the B. Dimension 3 by 3. This one is 3 by 3. Yes, the same dimension. And the corresponding entry A sub 1 1 1. The corresponding entry 1. Yes. And the 0 should be x. So x should be 0. And the y here, look at the y. Y should be 5 and the z. Z is 1. It's okay. So now and our aim to get the new matrices. It's okay. We have and some matrices. Our aim is to get the new matrix. So how to get the generate the matrix? It's okay. New matrices. So let's define the operation on matrices. It's okay. And the first operation, matrix addition. What's the matrix addition? And so take the two matrices, A and B, but be careful and here and it should be and the same dimension. A and B two matrix, two matrix, n by n matrix. This one should be n by n, this one should be n by n. It's okay. And let's define the sum of the A and B. It's okay, A and B. So this one gives the new matrix and it's okay. So new matrix, say that and this one is C. It's okay, Cij. So how to and determine the any matrix? And let's define the C. C and our and the matrix A and B is okay. We obtain the matrix C. So how to determine C? And and first of all, you have to give the dimension of row and column dimension of these matrix. So if our matrix m by n A and the B is m by n, so and the C should be m by n. So if on the two matrix we have two matrix m by n, so the sum of and the A and B and denoted by C, C should be m by n matrix. So and also the next step, first step determine the dimension, and the next step and they give the all entry and the C is Cij gives the all Cij entry. It's okay. So what's the Cij entry? How to get? And the Cij and means the row I and the J column, and the C this one. It's okay. And look at this one, and the row I this one, and the J this one. What's the and the D's entry? It's okay. Located in in row I and column J. It's okay. Our aim is to find these entries. It's okay. How to find? And the corresponding entry should be the sum of the corresponding entry. It's okay. Cij, the sum of the corresponding entry of A and B. It's okay. And adding corresponding entry of A and B. Let's give an example. It's okay. And first, and this one is A. This one is the matrix B. It's okay. What's the A plus B? A plus B. It's okay. So, and dimension and 2 by 3. So 2 by 3 matrix. So what's the first row and the first column entry? This one. So, and the first row and the first entry is 0 and 1. So this one is 0 plus 1. This one should be minus 1, 1. So 0. And the 3 plus minus 3 is 0. And the 2 plus minus 1, 1. 2 plus 1, 3, and 3 we obtain. It's okay. So, and the entry, how to get the entries of C and by adding the corresponding entries of A and B. It's okay. But, and here, critical point, it's okay, critical point, our matrices have the same dimension, row and column dimension. Otherwise, undefined. Otherwise, A plus B, undefined. Undefined. It's okay. It is not possible to get the matrix. Should be the same and dimension, row and column dimension. It's okay. It is important point here. Yes. So, and the natural question, we have the one operation, addition. It's okay, addition. So, and what can you say about the properties of the matrix addition? It's okay, this operation. So, and the sum and the properties is similar to the properties of the real numbers. It's okay. And for example, take the 2 and the real number. Sorry. A and B, real numbers. So, and if we obtain new real number C, it's okay. This one is real number, should be. And here, yes, and they take the 2 matrix, A and B. We can use the always and the capital and the A and the 4 matrices. It's okay. And this one is denotes the real numbers, but capital A denotes a matrix, and this one is a matrix. It's okay. M by n matrix. It's okay. This one. So, and we know that take the two real number A plus B, always B plus A is a commutative, and these and the properties is valid for matrices or not. And means our question, take the 2 matrix, it's okay, compute this one, and they change the order, and the B plus A or not.
Yes, it is true.
Sorry? This one is true or not?
True.
True. What's the reason? Look at the definition. Because what is the A plus B? A plus B. And how to get the entries of the first and the row first column, and 0 plus 1. It's okay. And also we know that, and this one is real numbers, and 0 and 1, and so this one is equal 1 plus 0. This one is equal 1 plus minus 1. So means, and this one gives change to order, we obtain B plus A. It's okay, because and the addition and here and this one is commutative, operation is commutative for real numbers. So use and this property here, change the order, so we obtain B plus A. It's okay. So and the matrix addition is commutative. It's okay, commutative. But here be careful and they take the matrices here and at the beginning, and they should be the same and the dimension n by n. N by n. It's okay. Otherwise, it is not possible to say the design. For example, take the design is 1 0 and plus and 2 1. Take this matrix and this one. It is possible to and write the result and this one. This one is undefined. Undefined because this one is 2 by 1 and this one is 1 by 2 matrix. Undefined. It's okay? Undefined. So this one it is important and it should be the same and the dimension, row and column dimension. So A plus B always is equal B plus A. And also associativity is valid than this one. And also, sorry. And there exists a unique n by n zero matrix for every n by n matrix A. Because take the any matrix n by n, it is possible to construct the zero matrix dimension n by n. So, and the same and the dimension A is n by n, and the zero n by n matrix, we can construct and the zero matrix, all entry and the zero should be. So yes, there exists a unique n by n zero matrix such that A plus 0 plus is equal 0 plus A is equal A. And we know that and this property for real numbers, take the any real number R, it's okay. It is, and we know that A0 0 plus A is equal A. It's okay. This property is valid and the for and the matrix is here. It's okay. There exists the unique zero matrix. It's okay. And also the next property, take the n by n matrix. It's okay. There exists a unique n by n matrix B such that A plus B is 0. It's okay. And start with A. Our aim is to get the matrix B and is such that A plus B is 0. Yes, it is possible. And the B is noted by this notation. It's okay. It's called the negative of matrix A. It's okay. A plus minus A is equal minus A plus A is 0. How to get the minus A? And means take the matrix A and multiply by minus 1 all entries. Okay. And so we can construct the minus A in here. And this one is 2 by 3 0 matrix. This one is 2 by 2 matrix. For example, this one is a matrix. So, and the 0 matrix for A and this one. It's okay. We obtain A. So now let's give and the another and the operation. It's okay. Multiplication. And multiplication by scalars. It's okay. Another operation on matrices. Let's define this operation and take the n matrix. Our aim is to produce any new matrices by using this and the operation. It's okay. This operation. So take the n matrix and the A. M by n matrix. It's okay. M by n matrix. And take the n scalar R. R. We have the two matrix A. One matrix A. It's okay, and we have this matrix n by n matrix IJ, and take any real number. It's okay. Our aim is to define multiplication by scalars. This one is scalars, and take the n matrix, and the multiplication by scalars gives new matrix. New matrix is denoted by this notation, R times A. It's okay, R times A. This one is a matrix. So what can you say about the new matrix? It's okay. If R matrix A, and they use a different color, and for example, this one is n by n matrix. It's okay. Any question? No, okay. We have the one matrix, one scalar. It's okay. So our aim is to get the new matrix, R times A. Let's define the multiplication by scalars. What is the this matrix, new matrix? If our matrix A is n by n, and the R times A should be n by n. So the next step, to define the all entries of this matrix. This matrix, for example, is denoted by B, new matrix. It's okay. So our aim is to give the dimension n by n. Yes. The next one gives the entry Bij. So what's the Bij? It's okay. All entries. Let's define. It's okay. Now, so what is the end of this one? And entry Bij, how to get and the Bij, and take the corresponding entry of A and then multiply by R. It's okay. So we obtain the corresponding entry of new matrix. It's okay. So and this matrix is obtained by multiplying, yes, each element of A by R. It's okay. Let's give an example, and then first of all, let's give the sum and the definition. But here, the next one, A and B are n by n matrices. It's okay. Let's define then this one. It's okay. A minus B. What does it mean, A minus B? A minus B means sorry. Let's define A minus B. What does it mean, A minus B? We don't know minus here. It's okay, operation. We know that A plus B, addition, but we don't know A minus B. And what's the A minus B? A minus B and means take the matrix A, use the operation, addition operation, and use the multiplication by scalars. And take the matrix B, use the this scalar minus 1 multiply by and this one. It's okay. So A minus B is equal A plus scalar multiplication by minus 1. It's okay. So what does it mean? First of all, and compute and this one scalar multiplication, and then sum of the A and new matrix. It's okay. This one. And and this one is called and the difference of A and B. It's okay. But here and the scalar multiplication by scalar multiplication, but operational here. Look at then the next one, and then we will give the example. And this one is and the general case. It's okay. General case of then this one. It's okay. Scalar multiplication. And take the, for example, matrices A sub 1, A sub 2, A sub k, but here all of them have the same dimension, n by n. It's okay. All of them n by n matrices, same dimension. And then take the k and the matrix and also k scalar. C1, C2, Ck. It's okay. The number of scalar k, the number of scalar number of scalar and the number of and the matrix K. It's okay. So and all scalars, real numbers. Then look at this expression. C1 a sub 1, C2 a sub 2, Ck a sub k. So what does it mean this one? What does it mean this one? Take the first matrix, take the first scalar, use the multiplication by scalar. It's okay. And then we obtain the first term and this one. It's okay. And the next one, another scalar multiplication and the next one. And then compute the sum of and this one, this one, and this one. It's okay. This expression is called the linear combination of the R matrices. It's okay. And here, C1, C2, Ck are called the coefficients. It's okay. Coefficients. It's okay. Let's give an example to understand the linear combination of matrices. It's okay. For example, take the two matrix and the A and B here. A, this one. A 3 by 3 and B 3 by 3 matrix. It's okay. So our aim is to compute these linear combination. This one is the linear combination and the scalar here C1 is -1 and here C2 is 3 over 2. It's okay. Compute this linear combination, please. It's okay. Yes. Let's wait and to take your answer. It's okay. What's this one is the scalar multiplication and also first of all you have to compute this one and the second one is second step and then we compute the sum of and these matrices. It's okay. Yes, compute please. Sorry. Yes, let's wait. It's okay. It is easy to compute to this one, -1. It's okay, -1 times A. And so -1 multiply by -1. And so means multiply all entries by -1. -1, 0, -2, -2, plus, minus, 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 minus. So, and the next step, compute to this one and means and the all entries multiply by 3 over 2. Yes, compute and so the next one use the addition operation. Yes. Compute please. Yes. What's the result? This one is a matrix, 3 by 3 matrix. So first entry, what's the first entry? 2.
2.
It's okay. The next entry, first row of the second column, this entry, what's this one?
-3 over 2.
-3 over 2. The next one?
-1 over 2.
-1 over 2. Write the second column, please. Yes, first entry of second column. This one.
-2.
-2. Sorry. Yes.
11 over 2. -5 over 2.
Yes.
minus 3, 2,
Yes.
and minus 7 over 2.
Minus 7 over 2. It's true? Everybody?
Yes.
Yes. Let's check the answer. Your answer. 2 minus 3 over 2. Minus 1 over 2. Yes. Yes, it's true. You are right. Okay. Yes. This one is okay. And so the next one, another multiplication is okay, another operation, matrix multiplication. If we take the two matrix, for example, A and B two matrix, and here, let's come back. This one is the scalar multiplication. It's okay. Take the any matrix and any scalar, so we obtain new matrix here. It's okay. This one. And here, take the any matrix A, take the any scalar, so scalar multiplication by scalar, this one. But here, take the two matrix. What is the multiplication of two matrix? A and B is okay, two matrix. So our aim is to get the A times B. It's okay, A times B. But be careful. And here, for example, A is M by P matrix. P matrix, and so means A contains M rows, P columns, and the B should be P by N, and it contains P rows and N columns, and means, and this one is important, and the point here is okay, if A is M by P, so what is the dimension of P? And it should be, and row and a column, it is not important, another and number n, but this one and the rows, the number of rows should be, if this one contains and the P columns, this one should be P, otherwise undefined. It's okay. So means if this one is A is M by P and A, and the B is, for example, K by N matrix. Is okay. And look at this one and this one. P should be K. P should be K. Otherwise, undefined. It's okay, undefined. So, and what is this and the multiplication? This multiplication gives new matrix, a new matrix, and the first of all, and this matrix is noted by C, for example. And how to determine this matrix? First, you have to give the dimension. So, if let's write, it's okay, and take the matrix A, matrix B. Our aim is to get the new matrix. Multiplication of A and B is C. It's okay. Our aim determine and this one. It's okay. First of all, let's give the dimension. If A is dimension M by P, and this one is defined, not undefined, so should be P by N is equal. So what's the dimension? Take this one and this one, M by N. So this one should be M by N matrix. It's okay? M by N matrix. And how to get M by N? This one and this one. It's okay? C should be M by N. So the next step, and it gives the all entry of C. It's okay? Cij. What's the Cij? So Cij, and here is the sum of and the corresponding entries and the multiplication. It's okay. How to get this one? It's okay. Let's write the A and B here. A this one, B this one. So our aim is to get C, but determine the matrix C. And first of all, let's find the Cij entry, arbitrary entry. So Cij, our aim is to find the entry Cij. And so what is this entry? This entry located in row I and J column. It's okay, this one. So, look at the row I of A. Order, it is important. It's okay. So, column J. So, catch the column J. It's okay. So, how to get the Cij? So, take the row I, column J. So, multiplication, the corresponding entry. So, S sub I1, B1J. S sub I2, B2J. And the next one, the last one, I sub P, the last entry, BPJ. It's okay. So sum of the, this one, it's okay. So we obtain Cij. It's okay, Cij. And means, what's the Cij? First of all, Cij. So write the all entry of all entry of ith row. What's the ith row of the A? First entry, A sub 1. And the next entry of row I, A sub 2. The last entry, A sub P, row I. And then look at the J column. Write the J column, the corresponding J column entries. It's okay? So, first entry, B1J. The second entry of J column, B2J. And the last entry of the J column, BPJ. So, sum of all of them. It's okay? This one. So this one is denoted by this notation. It's okay. Use the sigma notation from the k is 1 to p. It's okay. A sub ik bkj. It's okay. Yes, and let's stop here, and then we will give the example and the next day. This day. It's okay. Any question? No question?
Hocam burada neden
Yes.
toplama işlemi gibi yapmadık da şöyle farklı bir şey oldu?